In last few chapters, we have derived solution of a partial differential equation as an infinite series. It is also possible to find solution of a partial differential equation as integral superposition in terms of an auxiliary function which is known as Green's function. The advantage of taking integral solution of a partial differential equations are as follows. Firstly, the integral representation helps us to visualize the analytical structure of the solution which may be obscured in an infinite series solution. Secondly, it is sometimes easy to evaluate the integral compared to find the sum of an infinite series. Thus, chapter 8 is devoted to the study of Green's function. Using Green's function, we shall find solution of a partial differential equation. The entire chapter is divided into two modules. In module 1, we shall define Green's function. We shall discuss some properties of Green's function. In addition, we shall derive Green's function for Laplace equation. In module 2, we shall discuss about the Green's function for solving heat equation and wave equation. Now we are going to the first slide show of module 1. Before going to the discussion on Green's function, I am first defining a special function which is called Dirac delta function. The Dirac delta function, which is denoted by delta, x minus xi y minus eta equals to 0 for x not equals to xi and y not equals to eta. This is Dirac delta function in two variables. And property number 2, it says that integration of delta over x and y in the region R epsilon, where R epsilon is the region x minus xi whole square plus y minus eta whole square is less than epsilon square. So, in this region the integration of delta is equal to 1. And the third property, which is very important, we shall use this property to find solution of a PD. The third property or property number C says that integration over R capital F x y delta x minus xi y minus eta dx dy is equal to f xi eta for arbitrary continuous function f in the region capital R. The delta function is a symbolic function and is often viewed as the limit of a distribution. Suppose delta x minus xi and delta y minus eta are one dimensional distribution, then we can prove that integration of f into delta x minus xi into delta y minus eta dx dy is equal to f xi eta. And if we see the result 3 and 4, we can conclude that delta x minus xi into y minus eta is equals to delta x minus xi into delta y minus eta. So, in equation 5, we have shown that Dirac delta function in dimension 2 can be written as product of Dirac delta function in one dimension. Now, this result can be generalized if x is a n dimensional vector x1, x2, xn and xi is a n dimensional vector xi1, xi2, xin. Then we can prove that delta x vector minus xi vector is equals to delta x1 minus xi1 delta x2 minus xi2 into delta xn minus xin. Suppose we have a non-homogeneous partial differential equation which is written in equation number 7, L ux equals to fx where capital X has components x, y, z and L is an arbitrary linear partial differential operator and Fx is some known function, and we want to find the value of Ux for which equation 7 is satisfied. Now we shall show how can we introduce the concept of Green's function to find solution of 7. The Green's function g, which is function of x and y, is defined as L on g is equals to delta of x minus y. Therefore, the Green's function is such a function which will satisfy equation 8. Now we multiply equation 8 by Fj and integrate over a volume V, where dV is dxi, deta and dxi. So, integration over V Lg Fj dV is equal to, the right hand side is integration delta x minus xi Fj dV, and this is equals to Fx using the property of delta function. Now, if we see the left hand side of this relation, L is an operator which is operated on function of capital X only. So, we can interchange the operator L and the integral operator in equation 9. So, the left hand side of equation 9 becomes L operating on integration over V of g f dV is equal to Fx. Now, the quantity within the square bracket can be assumed as our Ux or our required solution. Therefore, solution of the given equation, which is written in equation number 7, can be written as Ux equals to integration over V g x xi into f xi dV, where g is the Green's function and it's play the role of a kernel in this integration. So, in this way we can find solution of a non-homogeneous partial differential equation using Green's function. In the last section, we have discussed how to find solution of a non-homogeneous partial differential equation using Green's function. But it is also possible to find solution of a homogeneous equation using Green's function. In the present section, we are going to derive Green's function solution of Laplace equation. Now we are going to our slide presentation. First, we are considering an interior Dirichlet problem. Suppose the values of u and del u del n, where del u del n represent the normal derivative of u, are known at every point on the boundary S of some finite region capital V. And it is also given that u satisfies the Laplace equation Laplace square u equals to 0 within the region V. Let P be an arbitrary point within the volume V, and we are interested to find the value of u at the point capital P, that is u at P. For that purpose, we surround the point P by a sphere sigma with center at P and having radius epsilon, as it is shown in this figure. So, this is point P and this is sigma, and the radius of the sphere is epsilon. Let capital sigma be the region bounded by sigma. Let OP be the vector smaller, which you can see here. O is the position of origin and P is a point inside V, and OP is the vector smaller, and Q is an arbitrary point in the region V, and OQ vector is Chi. And let V dash be the region V minus sigma, and S dash be the boundary of the region V dash. So basically S dash is union of, if you see the figure, S dash is union of S and small sigma. Now OQ is the vector Chi, and we choose U dash as 1 by mod of R minus Chi. If U and U dash are twice continuously differentiable function in capital V, and if they have first order derivatives on the surface S, then using Green's theorem we can write that volume integral of U Laplace square U dash minus U dash Laplace square U is equals to surface integral of U del U dash del n minus U dash del U del n ds dash, where n is the unit normal vector to ds dash, and it is drawn in outward direction in s dash. Now Laplace square U is equal to Laplace square U dash is equal to 0 within V minus sigma. Therefore, left hand side of equation 11 becomes 0. Now if we see the right hand side of equation 11, this S dash is nothing but union of surface S and small sigma. So this surface integral can be written as integration over S U del U dash del n minus U dash del U del n ds plus surface integral over sigma of the same quantity is equal to 0. Here we have chosen U dash as 1 divided by mod R minus Chi. So in the next step we substituted the value of U dash. So the integral becomes surface integral over S U del del n of 1 by mod R minus Chi minus 1 by mod R minus Chi into del U del n ds plus this is the surface integral over the surface sigma of the same quantity. Now we can simplify this surface integral. If we take a point on sigma, small sigma, this small sigma is a point on the sphere of radius epsilon. Therefore, the value of 1 by mod R minus Chi is equal to 1 by epsilon, and derivative of this 1 by mod R minus Chi is equals to 1 by epsilon square. Also, a surface element on sigma can be written as d sigma equals to epsilon square sin theta d theta d phi. Therefore, on sigma we can write U xi is equal to U r plus r into grad U. So, that equals to U r plus U del U del x plus y del U del y plus z del U del z. So, this equals to, if we substitute the values of x, y, z here, it takes the form which you can see here. So, this term can be considered of order epsilon. So, on sigma u xi is equals to u r plus term of order epsilon. Therefore, del u del n is equals to del u del n on r plus order of epsilon term. Now, think about this integral. Surface integral on sigma u del del n of 1 by mod r minus xi is equals to, now on sigma we derived that u xi is equals to ur plus the term order of epsilon, and value of del del n of this quantity is 1 by epsilon square, and d sigma is epsilon square sin theta d theta d phi. So, after substitution we obtain this simplified to u r. Since r is a constant, so we can take out the term u r from the integration. So, this is u r integration of sin theta d theta d phi over the surface sigma plus order of epsilon term, and after integration we obtain its value is 4 pi. Therefore, value of the integral u del del n of u dash is equals to 4 pi u r plus term of order epsilon. Now, if we evaluate this term, integration, surface integration of 1 by mod r minus xi del del n of u xi over the surface sigma, it becomes this. So, it simplified to the term. If you substitute the values of all term, del u del n becomes del u del n plus order of epsilon, and value of 1 by mod r minus xi is 1 by epsilon, and value of d sigma is epsilon square sin theta d theta d phi. So, after simplification you can see that this value of this integral is of order epsilon. Now, if we substitute 13 and 14 to equation 12, that means we are substituting the value of the surface integral over sigma, we obtain a relation which is written here, u r equals to 1 by 4 pi surface integral over S 1 by mod r minus xi del u del n minus u into del del n of 1 by mod r minus xi ds. So, from this expression, and we obtain this expression considering epsilon tends to 0. So, from this expression you can see that the value of u can be obtained at an arbitrary point P, which is denoted by u r, can be written in terms of surface integral of the quantity which is written in equation number 15, and to find value of u at P, we need to know the values of del u del n and u over the surface S. So, if these two quantities are known, we can find u at an arbitrary point P. Similarly, in case of exterior Dirichlet problem, we can obtain a relation which is given in equation number 15. Thus, we found that we need to know both u and its normal derivative on the surface S. But let us try to think the problem in some different way. Now, we consider a function which is known as Green's function, which is of the form g equals to h plus 1 divided by mod r minus xi. Now, we define a function g in this way, and we also assume that the function capital H is harmonic. That means H will satisfy the Laplace equation which is written here, del 2 del xi square plus del 2 del eta square plus del 2 del zeta square operating on H equals to 0 on V. And we also assume that the function g is such that the value of g is equals to 0 on the surface S. So, if g satisfies this condition, the function g is called Green's function. Now, in the preceding section, if we substitute u dash by the Green's function g, then value of u at r can be written in the form which you can see in equation number 18. Now, this g is not any arbitrary function, it will satisfy some conditions which are written in equation 16 and 17, and it is also given that g is 0 on S. So, if we use that condition, equation 18 reduces to the form equation 19. In equation 18 we put g equals to 0 on S. So, u r equals to minus 1 by 4 pi surface integral of u del g del n ds. Hence, the solution of Dirichlet problem is reduces to that of determination of Green's function capital G. So, in this form, in this solution, we do not need to know the value of normal derivative of u in the surface S. So, this is the advantage of finding solution in terms of Green's function. Now, I am going to discuss some properties of Green's function. It has one important property, that Green's function g, which is function of two variable, the vector r and vector xi, it is symmetric about these two variables. Now, to prove this property, we assume that the Green's function g has the form g is equal to h plus 1 divided by mod r minus xi, where h is a harmonic in V. Therefore, Laplace square g equals to Laplace square 1 divided by mod r minus xi, and its value is minus 4 pi delta r minus xi. Now, we assume 2 points P1, P2 in the region V. As you can see in this figure, we have taken 2 points, 2 different points P1 and P2 having position vectors R1, R2 respectively within the region capital V, and S is the boundary of the region capital V. We assume U1 as g at R1 xi is equal to h at R1 xi plus 1 divided by mod R1 minus xi, U2 equals to g at R2 xi equals to h at R2 xi plus 1 divided by R2 minus xi. We also have the Green's function at R1 and R2 is equal to 0 on the surface S, and Laplace square of g at R1 xi is equal to minus 4 pi delta R1 minus xi, and Laplace square g at R2 xi is equal to minus 4 pi delta R2 minus xi. Now, this is our famous Green's theorem, which convert the volume integral to the surface integral. Now, in this theorem, we substitute the values of u1 and u2. So, those values are substituted in the next step, and if you see the right hand side, That means the surface integral which you can see in this slide, its value is 0 on S, because by assumption G R1 xi is equal to 0 on S and G R2 xi is equal to 0 on S. Therefore, this relation becomes volume integral of G R1 xi into delta R2 minus xi. So, here we substituted the value of Laplace squared G as delta R2 minus xi. So, this equals to G delta R2 minus xi minus G R2 xi delta R1 minus xi dV equals to 0. Now, this integral can be separated. So, the first integral, value of the first integral is G R1 R2 and the value of the second integral is G R2 R1, and this value can be obtained using the property of delta function. Therefore, this equation gives G R1 R2 is equal to G R2 R1. So, this says that the function G is symmetric with respect to the argument R1 and R2. Now, I want to discuss another property of Green's function, and it is said that if the Green's function G be continuous and its normal derivative del G del n be discontinuous at a point R, then limit epsilon tends to 0, del G del n over the surface sigma is equal to 1. Now, we know the property of Green's function as Laplace squared G is equal to delta R minus xi. Now, we integrate both sides over the sphere sigma. Then we obtain the volume integral over sigma Laplace squared G dV equals to 1. Now, if you take the limit epsilon tends to 0, then its value will remain same. Volume integral of Laplace squared G dV equals to 1. Now, this volume integral can be converted to the surface integral using the divergence theorem. So, it gives that limit epsilon tends to 0, surface integral of del G del n ds is equal to 1. So, this is the required proof of this theorem. Thus, in module 1 of chapter 8, we have learned how to find solution of a non-homogeneous partial differential equation using Green's function. We have also taken a homogeneous equation. For example, we took Laplace equation to find its solution using Green's function. There are many linear differential equations which can be solved using Green's function method. Thus, we end this module.